Hello, class. We are moving through the book at a good pace, because we really have three things that we're trying to do all at once here. Learn all about statics, dynamics, and solid mechanics. We can't learn about everything, but we'll learn about quite a bit of it. So the next lecture that I wanted to get into is how do we use the cross product, right? And you probably always heard that moments are force times distance, but that's not true. Moments are not force times distance. In fact, when we look at moments, because moments are a vector, moments are the distance vector crossed with the force vector, right? Distance times force. And we're talking about vectors here, so we're talking about a certain types of multiplication, and that's going to be the cross product, not the dot product. So we know a couple things. We know that if I was to, let's say, I had a beam that was coming out the side of a building. I'm just going to draw a beam here. I had a beam that was coming out the side of a building. Now, we know that this beam, which is embedded right inside this building with concrete all around it, this beam that's coming out of this building has a force, right, applied to it, right, at a certain point that's now, if the force was going in this direction, right, perpendicular to the beam and straight down. Well, I didn't draw it, I guess straight down. There you go. That's a little straighter. Doesn't quite show up on the TV screen as it does here, but we've got a force now, right? A force that's going down, and I think everybody can see that force then, if I was to draw an axis through the side of this force is going to cause this beam to deform in this way. And so really what we have is we have an applied moment right at that point, right? And how far is the distance away from it? Well, you might say, well, the distance is out here and then it comes down a little bit, but does that really matter? Does it matter if it's down here or if it matters if it's up here? No. The principle of transmissibility tells us that if we move a force along its line of application to the rigid body that it's attached to, that it's still always going to create the same moments and forces throughout the body, right? So we've got a moment here. I've got a moment. Now, here's the interesting thing, which direction is the moment going to point in? I'm going to show you right now. The moment is perpendicular, right? So we've got a force. That force is in the minus j y direction, right? So I'd say it's minus j hat. That's the direction that's in. And what's the distance vector? Because isn't that what it is? It's the distance vector times the crossed with the force vector. Distance vector crossed with the force vector. And so what is the distance vector? Well, let's say that this, right, this point right here is O. And the place where this is applied is A. Then the distance vector is always from O to A. That's the distance vector. And you can see here that the distance vector is really just this length. Let's give this length an actual thing. Let's say it's 5, right? 5 meters. Oh, and what is the force? Let's say that the force is 80 newtons, right? So 5 meters, 80 newtons. Let's do the math now. First of all, we want to find out what the force. Well, the force is 80 newtons, but in the negative j direction. So let's write that force out. Oh, I forgot to put the timer on. I think I've been doing this about 5 minutes, maybe not even that. So let's just pop that. Go, get that started. That's good. Just in case we go too long. Probably not going to happen. It's a Sunday evening, but we do have a whole topic to cover. So, and it's a very interesting and important topic. So, let's figure this out. So, 50 or 80, we've got minus 80 newtons J hat, right? Because it's in the negative direction. Now, what is this? Now, if this is my y direction, right, because we said that that's the negative y, I'll say that this is my x direction, and this is going to be my z direction. So let's say that this from here to here is going to be plus 5, right? So from 0 to 5 would be plus 5. So r, going from the point we're summing the moments about to the point at which the force is applied, is going to be 5 meters I hat. Okay? Now, I think that everybody can see that R cross A, right? R cross F. What's that going to give us? Let's lay our hands along the X direction, roll our fingers toward the Y direction, and our thumb is going to be pointing in the Z direction, isn't it? So we would assume that it's going to be a K hat, wouldn't we? Because this is the thing. What we're really looking at with the moment is this is the moment, this is the magnitude, but what we're really saying is that that is a magnitude of a torque that is going to go around in that direction. Now, is that going to be a positive or a negative, right? Now, I've got a negative 80 newtons there. Let's not forget that. Because as you can see, this is going to pull down. This is going to pull it in the clockwise. And we know that counterclockwise is positive, clockwise is negative. So I'm assuming I'm going to have a negative moment here. Let's actually do the numbers and see. So the moment about O is going to be R sub OA, which is 5 meters I hat, crossed with F, which is minus 80 newtons J hat. Well, 5 and minus 80, right, is going to be minus 400. And I cross J, let's just draw our little diagram up here that Beer and Johnston gave us. I hat, J hat, K hat, right? I cross J gives me positive K. So it's going to be minus 400 Newton meters. And what is a Newton meter? A Newton meter is a joule, right? So minus 400 joules K hat. Does everyone see how I did that? We're going to do one that's a little more complicated than that. And in fact, it's not all that much more complicated, but it's still going to be two-dimensional. What I want to do is I want to draw a flange on the side of a building. So let's just look at the schematic that I'm going to draw here. Here's a building, right? And embedded in the side of the building, I'm going to draw this flange. It's not really just a two-dimensional little flange here, right? It's going to have, it's going to look like this. So it's not a big flange, but we want to find out what the forces are on this flange at the building, at where it's connected to the building, and where we feel that it is most susceptible to have the greatest moment. And so let's say that you're in a design team, right? And you've got this flange here. And you note that there's two different forces on the flange. There's a force that's pulling the flange down this way at a 45-degree angle. I'll just put a little thing there. Then we've got another one that's sort of pulling it up at a 60-degree angle in this direction. Both of these are relatively the same. Right? This is a steel flange, so we don't have to worry about that. But we want to just look at where the main forces are and the moments. We're really concerned about the moments between these 2 points, point A and point B. We know that these are attached, right in the center of both of these. And we know that the thickness of the flange that we're looking at is going to be 2 centimeters. Okay? It's 2 centimeters. This is going to be a 300 Newton force. And this is going to be a 500 Newton force. Remember what we've got here, right? This is going to be, I'll call this theta, and I will call this, it doesn't matter which one I call it, but I'll call this alpha. So alpha equals 45 degrees, and theta equals 60 degrees. All right, theta being this angle right there. All right, so we want to break those force. These are 2 different forces. This is I'll call this F1, and I'll call this F2. So we've got F1 and F2. We have to figure out what the components of F1 and F2 are, right? Because we're going to have to cross multiply those with the distance too. Now I haven't given you all the distances. I've only given you that as 2 centimeters. So this is going to be 2, 3, 4, 5, 6, 7, 8. This is going to be 8 centimeters from here to here. That's 8 centimeters. This is 2, 3, 4 centimeters from there. Boy, this isn't easy. Down to there. And then we'll also have 4 centimeters here. And you can figure it out too, because it's just 2 centimeters off, so that's 8. So this is going to be 6 centimeters there. And then up here, we're going to have, boy, I can't even figure that out. 1, 2, 3, 4, let's say, let's say 5 centimeters right there. And of course, this being 2 centimeters less than that, because it's 2 centimeters wide all the way, the flange. These eye holes are right in the center of those areas, so we'll have to take that into account when we're doing our distance vectors to those 2 things. And moments just add. And so we want to sum the moments about A, and we want to sum the moments about B for those 2 things. And so let's just look at that. So first of all, we have to know what F1 and F2 are and their components. So F1 is going to be 300 newtons, right? And we want to see, what is it in the X direction? So we know that alpha right here is 45 degrees. I probably should have made that something different. We probably should make that just so that, because it's going to be the same. Otherwise, you might, let's not say 45. Where else did I? No, nowhere. So let's not say 45. Let's say 40. All right, 40 degrees. And that way we can take the cosines and stuff. So it's going to be the cosine of, because we're looking at it this way, so we're going to see, we just want to break this down into its two components, right? We're going to have one going this way. We're going to have one going this way. We know that that's going to be positive in the x direction and negative. And we know that this angle right here is going to be 40 degrees, right? 40 degrees. So if alpha is 40 degrees, then we want the cosine of 40 degrees, right? And that's going to be I hat. And then we know it's negative going down here, so it'll be minus 300 newtons times the sine of 40 degrees, j hat. Does everyone see that? So that's what F1 is going to be. I'm going to leave a little room there. Actually, we could just you know, pop that in right now, really. 300 times the cosine of 40 degrees is 2298. Wait, is that right? Cosine of, no, that can't possibly be right. 300 times the cosine of 40 degrees equals 229.8. Let's say 230. I'm going to round that off a little bit and say 230 newtons in the x direction, and then minus 300 times the sine of 40 degrees gives us 192.8 newtons j hat. So that's what F1 is going to be. Excuse me for a second. I'm just going to grab a little sip of this nice warm tea here. Well, that was delicious. Now, we've got that, and I just want to circle this as F1. So we know, right, what F1 is in numerical form. And then F2, right? Figuring F2 out, we do it exactly the same way. We know that theta now is going to be 60 degrees. So this is going to be the cosine of 60 degrees, isn't it? Because we're going to break this down into its two components. We're still just talking about two-dimensional moments and stuff like that, but you know, it's good. It's good enough because you've got all that phasor background, and so you know how to change from rectilinear into magnitude times an angle, and that's what we've really got here. We've got a magnitude 500 newtons, and then we've got an angle there that's 60 degrees. So 500 newtons times the cosine of 60 degrees is going to give me oh my goodness, 500 times the cosine of 60 degrees is 250. So 250 newtons I hat. And is that right? Is that positive? Yep, because look at that component. That component's positive, and then the y component is going to be positive as well. And of course, that's the sine. So I hat, and then plus, and it's going to be 300 times the sine of 60 degrees, or 500 times the sine of 60 degrees, and that gives us 433 newtons in the positive j hat direction. Now, there's a couple things that we've really got to look at, you know, when we're doing the moments here. First of all, we want to look at the moments, right, and see what the moments would be, the applied moments, these two applied moments. So the first moment that we want to see is the moments about A. Right, so A, what's the distance to F1? Well, for A, it would be 1, 2, 3, 4, 5, 6, 7 I hat, right? So R sub A, let's put that in there. R of A. Now, should we give this an actual name here? Let's call it D. R to D. So the distance vector from A to D is going to be 1, 2, 3, 4, 5, 6, 7 centimeters, right? So 7 centimeters I hat. And then minus 1, right? Because we're going down 1 from A, minus 1 J. So minus 1 centimeter J hat. All right. Now, how about to the other one up here? Let's call that point E, right? So if that's point E, what's the distance to point E in this two-dimensional framework? Because now we're using A as our origin, right? Everything is from A. A is our origin. Later on, we're going to look at B as our origin, but right now A is our origin. We're summing the moments about A, not about B, not about O, about A. So the second one would be the distance vector from A to E, right? Let's see what that is now. Now, how far do we have to go out? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have to go 10 out because I've got 8 plus, no, isn't that, let's see, that's 8. Yeah, because that's 5 up there, so that's 3. And that's 1 off, so that's 2, 2, 8, 10. Okay, so I am right. 7, 8, 9, 10. Yes, so it is 10. So it's 10 centimeters I hat. And then how far up from A do we have to go in the Y direction, right? 1, 2, 3. So plus 3 centimeters J hat. Does everyone see how we got those distance vectors from this diagram that we've got over here? And everybody can see, you know, what the individual, I've just used these individual quadrille or, you know, quarter-inch things as 1 centimeter. So you can see that I've sort of used it to scale to draw this flange coming out and the 2 different cables that are attached to the flange in those 2 different directions. All right, so now we have really everything to find the moments, the applied moments about that point A. And that's what we want to find out. We want to find out where is the greater moment, at A or at B. So we're going to sum both of these at both of those 2 locations. All right, so I have R sub AD, right, crossed with F1. Plus, let's put some parentheses around there, R sub AE crossed with F2. Does everyone see what I've done there? Okay. You know, I'm not going to write all of these out again, but what I am going to do is I'm going to just mark these off. And in fact, since I have F2 right here, I'm going to include F2 inside my red rectangle. And I'm also going to include these 2 in their own rectangles so that I can easily refer to them. And I know you you people are colorblind, you can't see the red, but it's there. Those are the rectangles. I did them in red. So let's go and do this one at a time. So R sub AD times F1. So I've got 10 centimeters I crossed with 230 newtons I. Well, we can't do that because I crossed with I, right, gives us nothing. But now I've got 10 centimeters I crossed with 192.8 newtons J. Oh, that gives me something, doesn't it? So that gives me 1,928. So let's write this down. So moments about A are going to be 1,928 Newton centimeters, right? Isn't that what it is? Newton centimeters. And then I cross J gives me K, right? As we would expect. In fact, all of the moments that we get here should all be K, because they're all coming out of the paper, right? Every moment, the moment at A is going to be like this. Now, what that means is that the actual length of this is going to be the magnitude of the moment, right? But the moment itself is going to either be going clockwise or counterclockwise about this point. And I would say that this, the applied moment here, this pulling down is probably going to cause a clockwise or a negative moment, right? So anyway, let's go back to this because I've got 10 centimeters I crossed with minus that. So an I cross J. So this should be a minus, right? Because I'm minus 1,928 and then times I cross J, which is K, positive K. So we've got minus 1920. We still got to do the other one, though. We've got 3 centimeters, right, J, crossed with 230 newtons, I. So let me just plug that in there. 230 newtons times 3 centimeters gives me 690. Now, wait, excuse me. I did the wrong one. I've got 1, minus 1. Oh my God, I did that. Well, at least, and you're probably all saying, hey, he's doing the wrong one. That's right. This is the one that I wanted. That's why I put him up there. Well, that took about 2 seconds, so that doesn't bother me too much. I didn't get too far off there. And we can quickly figure that out because we've got 7 centimeters times 192.8. So let's just do that. 7 times 192.8 gives me 1349.6. So I'm going to say 1350 Newton centimeters K, and that's the first one. 7 centimeters times this. Now we've got minus 1 centimeter J times 230. So that'd be minus 230. Oh, this, by the way, is a minus 2. That would be minus 230, right? Because I've got minus 1 times 230. But then I've got J crossed with I, and J crossed with I is going clockwise, so that would give me negative K, right? So the negative K cancels out with this negative, and so I get a positive 230 Newton centimeter in the K direction. All right. And so 230 minus 1350 is minus 1120 Newton centimeters. Now we don't really work in, and of course I'll put K there. We don't really work in Newton centimeters, do we? So we want to change that Newton centimeters. Do we multiply by 100 or do we divide by 100? Don't I really want to multiply it by this? Don't I really want centimeters in the bottom and meters on top? Don't I know that I've got 100 centimeters in 1 meter? Don't the centimeters then just cancel out like that? So I've got to divide by 100, don't I? Well, it's 1,120, so if I divide by 100 and my decimal points here, 1, 2, that means I've got minus 11.20 Newton meters in the K direction. Does everyone see how that works? Excellent. And so that's what our moment is. I'm just going to put that here. That's our moment about A. That's our applied moment about A. Now, is it going clockwise? Yes. Yes, it is. Now let's do the same thing and do our moments about B. Again, we have to find out what that distance is. So we need R from B to D, and we need R from B to E. Shouldn't be too hard because this is just going out here, but instead I'm going up 1. So that's just going to go 7 centimeters I hat plus 1 centimeter J hat. Does everybody see that? That's a 1, by the way. And then if I'm looking at B to E, I'm going out here. It's still going to be the same distance out, which is going to be 10, right? 10 centimeters I. Did I? Wait a second. What? Let's see. Do not do lectures late at night, even. So what did I get? Oh, wait a second. So this is the 7, and that's the minus, and I forgot to do the RA, so I'm going to do it right here. Oh, my goodness. But this still applies. I'm just going to have a different number there for a second. So I've still got to add on R sub A, which is 10 centimeters. Oh, my goodness. And then on to F2. So 10 centimeters times 433. That's going to give me 4,330 Newton centimeters. In the, yeah, I definitely will stop for the night in the K direction. And then I've got 3 centimeters J times 250, so that's 750. But J cross I is minus, so it's going to be minus 750 Newton centimeters K hat. And what that gives me when I add all of those together, so 4,330 minus 750 minus 1350 plus 230 gives me 2,460 Newton centimeters. All right, 2,460 Newton centimeters, or if I wanted to put it in Newton meters, 2460, and that would be positive. Excuse me, there we go. So yes, in the end, I actually figured out that I was doing something wrong along the way. Way too late to be doing a lecture. Got to do them in the morning where I'm much more on top of it. Let's do the moments about B, though, which is just as good. We figured out what this is. So 7 centimeters plus 1 centimeter. Let's do the one to B. That's still going to be 10 centimeters I hat. But now it's going to be an extra 2. So instead of it just being 3 centimeters, 1, 2, 3, I've got another 2. So it's going to be 5 centimeters J hat. All right. F1 and F2 aren't going to change, so let's just do this. So B to D, that's 7 centimeters times 192.8, still the same thing. It's going to be minus 1350 Newton centimeters K hat, right? That first one is going to exactly be the same. That's the 7, and then now I've got plus 1. So plus 1 times 230 is, yes, plus 1 times 230 is 230. And then I have J cross I, which is going to give me minus K. So that's minus 230 Newton centimeters K hat. And then let's do the other one, 10 centimeters I hat times 430 newtons. It's still the same as it was before, 43 because it's J, I cross J, so 4,000 plus 4,330 Newton centimeters K hat. And then the last one is going to be 5 centimeters now times this. So that's going to be 1,250, right? 1,250. And then J cross I is minus, so minus 1,250. All right, Newton centimeters K hat. All right, so we've got that. Now we want to add that up to find out what the moments are about B and see which one of these two has the greater magnitude of moment about it, that we would have to beef up that area of the flange, right? Maybe we have to fillet this area of the flange, or we have to fillet this area of the flange, or something like that to help with it restraining the applied moments. But first of all, let's find out what which one is bigger. So we've got 4,330 minus 1,350 minus 230 minus 1,250 gives me 1,500 Newton centimeters K hat, or 15.00. Let's put lines over that to show their significant digits. Newton meters K hat. So everybody see that? How you know, we figured out the two maximums. Yeah, much different. There should be a decimal point there. Much different between these two, isn't it? As you can see, we've had quite a savings when we look at the bending moment here. So the place that we're really concerned about this is going to be A, not so much B. All right. Now, what we're going to do is extend on this lecture, and we're going to go into three-dimensional moments, and then see how we can figure out what those would be along an individual axis and stuff like that. So, got a lot, doing a lot. Make sure you're working on those home sets too. Okay. This has been a little longer lecture, and it's Sunday evening, so won't be doing another lecture tonight, but I'll see you tomorrow morning. All right, bye.